So in the last class we are discussing about the thermodynamic equilibrium. So we'll continue with that. So what we have discussed there is, so thermal equilibrium we are discussing. So in we compared it with the mechanics. So in mechanics, when net external force and the torque on the body is 0, then it is called as mechanical equilibrium. But in context of thermodynamics, it is different. In context of thermodynamics, we say that the variables that is describing the state should be constant with time, then only it characterizes the system to be in equilibrium. So some of the macroscopic variables that I introduced are density, viscosity, moles, pressure, volume, composition. Viscosity is not that important in case of this system, what we will be going to discuss in next few lectures, but the density, moles, pressure, volume are one of the important variables. So nature of, we have discussed that what should be the nature of wall, because nature of the wall is important to describe the equilibrium. So if it is the adiabatic wall, if a system has having the adiabatic wall, then it is already in the equilibrium, because it is not exchanging with the surrounding. If this is the system and this is the surrounding, then when there is no exchange between the system and surrounding, then the walls are called to be a adiabatic wall, and so this system is already in equilibrium. But in case of diathermal wall, when there is an exchange of energy between the system and the surrounding, when there is a exchange between the system and surrounding is allowed, then it is a diathermic wall or diathermal wall. So that is a diathermic wall, and here equilibrium is achieved when some of the variables stop changing with time. Initially, when it comes in contact with surrounding, there is a change, due to which there is a change in the pressure or the volume of the system, but as soon after some times this will get converged and it will become constant, and so it reaches the equilibrium. So I will be going to explain this thermodynamic equilibrium with this diagram. So let's say we are having a body, so we have this container and we are having this wall. Considering that this whole system is insulated with the surrounding, and there is another system, the walls, these walls are also, so these walls are insulated. And these walls are also insulated. The only difference is between the wall that are separating A and B. Here let's say this wall is adiabatic and this wall is diathermic, as I already discussed. So in a more formal way I can write, so adiabatic is the type of wall, so it is an insulating wall that do not allow exchange of heat, while diathermic, it is a conducting wall that allows heat to flow from one system to another. So here we have taken two different gases A and B. So in this case it is a adiabatic wall, in this case we are having a diathermic wall, we have PA, VA, PB, PB. Those are the thermodynamics macroscopic variables that I already discussed. So now here if you see, there is heat is not allowed to exchange in between A and B in case of when there is a adiabatic wall, which means to say that A and B, it's that I already tell. So A and B are already in equilibrium with each other, so they are not exchanging anything. But in case of diathermic wall, heat is allowed to exchange between A and B, and due to this, there if initially it has PA, VA, PB, VV, then these variable in at equilibrium will going to change to, so this become let's say P prime A, V prime A, and this becomes P prime B, V prime B. So these, there is a change in the this macroscopic variables before it comes into the equilibrium. So this change occurred, and now it is at this A and B, this system is in equilibrium. So now the question arises, what characterizes the situation of thermal equilibrium between the two systems? So the question is, what characterizes the equilibrium between the two systems? So you can guess that answer. So you may guess and what you can guess? Let's guess it. So you can guess it. It should be a temperature, that is the important property that is describing the equilibrium. So the two systems, so two gases A and B are in equilibrium when the temperature of A should be equals to B after some time, because there is exchange of heat and there is a diathermic wall, and that is which is allowing the heat to transfer from A to B, and after some time there is a due to this transfer of heat, it reaches the equilibrium, and due to which whatever the temperature initially of one body and the another body is at equilibrium, what happens is the temperature of the two body becomes equal. So this is what we understand intuitively. So we shall see how does one arrive at the concept of temperature in thermodynamics. So the zeroth law of thermodynamics will going to give a clue of it. So temperature is our guess, it's not coming from what we have learned so far. Zeroth law of thermodynamics will going to tell or will going to give the clue of how the temperature comes into the picture. So let's discuss zeroth law of thermodynamics. So let me write the definition, the formal definition of the zeroth law of thermodynamics. So it states that two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. So this is a bit confusing statement. For me also this is a bit confusing statement, but it is a formal statement. So the more easy statement for the zeroth law of thermodynamics if I have to give is, if A and B is in thermodynamic equilibrium and B and C is in thermodynamic equilibrium, then C and A must be in thermodynamic equilibrium. So that is the zeroth law of thermodynamics. So I will be going to describe the zeroth law of thermodynamics with one example. So what we did here is, we took, now instead of 2 gases we have taken 3 gases. So let us say I can draw this. So we will be having first system, so this is, let us say, C, this is A, this is B. So this is one and another one is the similar system, but again there is a difference in the walls. The walls that are separating A to B, B to C. So in this case, A and B are separated by adiabatic wall, while A and B with C. So this wall is conducting, or we can say diathermic. In the second case, this wall is replaced with diathermic wall, and C is insulated from A and B by an adiabatic wall. Now this wall is so imagine two systems A and B separated by an adiabatic wall with each other, and both of them is in contact with the third wall via conducting wall. So what will happen? What you think should happen in the first case? So there shouldn't be any exchange between A and B, that is very clear, because there is that is a adiabatic wall, but there is some exchange between A and C and B and C, and this exchange is there till it reaches the thermal equilibrium. So Zeroth law of thermodynamics clearly suggests that the systems A and B in thermal equilibrium, if the system A and B in thermal equilibrium, then there must be a physical quantity that should be equal for both, and that is what we called as temperature. So if A and B are separately in equilibrium, then TA should be equal to Tc and Tb should be equals to Tc, which implies that Ta should be equals to Tb. So here, if you change this wall, and these are two, now this is the after this you change the walls and we arrive these walls, and what happen is that this wall becomes adiabatic from diathermic and this wall becomes diathermic from adiabatic. So you will see there shouldn't be any exchange between all of this, because already it achieves the equilibrium. After achieving equilibrium, when we change the wall, we can see there is no change, because it is this ABC is already in the thermodynamic equilibrium. And so from the zeroth law of thermodynamics, we can say that there is a temperature that describes the thermodynamic equilibrium. So we'll end this discussion here. In the next lecture, we will be going to discuss heat, energy and work, and we'll go through quickly with all these equilibrium concepts in the next lecture. Thank you.